Okay, so now we're going to reverse the making of the acetal, and we do that through hydrolysis. So hydrolysis of acetals it's literally the entire mechanism we've already done. Forming an acetal, the only difference is that instead of using alcohol, in this case we're using water. So remember Le Chatelier's principle, whatever it is that you are pushing from one direction or the other, you want to add excess to one side, it forces it to the other side. So yes, technically this is going back and forth in equilibrium, right? So that could go both ways. However, sorry, that did not look very good. So we can go back and forth in both ways. That's the best way to draw that. There we go. But that's all we're doing is trying to push this using water, usually as a solvent, to try to push it fully to the hydrolysis product, otherwise known as the ketone or the aldehyde. So this mechanism should look very familiar, I hope. So if we have an acetal, basically these groups here are individually going to end up being the alcohols that you may have put on using the ketone to begin with. So in this case, what we do is we start with the electrons from oxygen. Those go and grab a hydrogen, leaving behind water, your conjugate base, whatever that may be. Remember, whenever you have H2O in the presence of acid, so if we have it in H plus, then what forms is H3O plus? So that's the reason why I'm using here H3O plus and water. So after we complete that transformation, this is a water molecule that leaves behind. Then the alcohol or the oxygen from the other ether comes down, and this alcohol leaves. So in this case, we're getting methanol out. That is because that's an Me right there. So it's just a methyl group right there. If you have a different kind of alcohol, that's what's going to leave. So this is just an example. Just making sure you know that. So your conjugate base in this mechanism is just water, but it's also your solvent, so it's very, very abundant. So if we have water, that will then attack your carbon from your carbonyl, although that's got a positive charge on that oxygen. Electrons go up. And now we have an oxygen right here with a positive charge. So let's recharge our acid catalyst. Water goes and grabs that hydrogen that's right there. And that's where we get our hemiacetal. So now we're almost back to the beginning. We just have to repeat the same sort of process with the other ether here that ends up being an alcohol. So that oxygen comes out and grabs a hydrogen. Electrons go back to the water molecule. The OH electrons come down, and this leaves. So again, you're getting out that alcohol. Finally, a water molecule comes and picks off that extra hydrogen. Electrons go back to that oxygen, and you're left with a ketone or aldehyde. Okay, so that's how we get rid of our acetal. Acetals can be used as protection groups for this very reason, because that entire thing is in equilibrium. So that's kind of nice. Sulfur nucleophiles we haven't really talked about yet, but they work very similarly to what we've seen with alcohol. So if you have two RSH, those will form sort of an acetal-ish type of compound. I'm sure that has a name. I can't recall it at the moment, where we have two SR groups right there. And just like we use protection groups with the ketone before, we can use that as well with sulfur, making sort of a 5-membered ring here. In the presence of Ronnie nickel, that's just the reagent. It has some hydrogen there as well. That will make this entire section come out, and you're essentially replacing that with two hydrogens here and here. So in that case, what we see is that you've got basically a reduction that's happening here, which we saw with Wolff-Kishner. This is just a different version of getting your reduced product. So let's recall some reactions that we've already done involving aldehydes and ketones. Remember, we can take that C-double-O bond right there. Oops, sorry, I had the wrong tool out here. We can take that C-double-O bond right there and turn it into an OH using either NABH4 methanol, or we can do that using lithium aluminum hydride followed by water or acid. And the mechanism, just to remind you, we take that hydride, the hydrogen from the hydride, will go and attack right at the carbonyl. Electrons go up to the oxygen here, and then the negative charge from the oxygen just goes and grabs the hydrogen from either acid or methanol, depending on what you have here. So I probably should have used methanol here, my apologies. We could also use Grignards with carbonyls. I think we've used these quite a bit now, so I figure that this is probably second nature to you, but I wrote out this mechanism as well. So remember that whatever R group you have, those electrons go here, electrons go up from that double bond into the oxygen, and then the acid or any proton source for that matter at all will come and grab, or the oxygen will come and grab that proton source. And so you end up with both the OH and the R group connected to the same central carbon there. You can also use what's known as a cyanohydrin. And basically all you're doing here is using HCN, remembering that HCN is something that is a weak acid that is undergoing equilibrium. So CN minus is present whenever you have HCN. Sometimes you see this reaction using KCN and some type of proton source. That's the same thing. It's getting at the same thing, okay? So in this case, what we end up with is a cyano group, CN, attached to the same carbon that where there's an OH. Okay, this is very similar types of mechanism where we have the electrons from the CN come to that carbon. Electrons go up to the oxygen, and then that oxygen comes and grabs a hydrogen from another molecule of HCN. So realize you've got a population of molecules here. Okay, so one of my favorite reactions for this time of year is what is known as the Wittig reaction. So a Wittig reaction is an interesting reaction using triphenylphosphine. So that's a PPH3, and I think that most of the time I refer to that with a lowercase h. Sorry, I don't know why I put the uppercase h there, but triphenylphosphine is PPH3. Okay, so we need to have some type of alkyl halide, and we need to have that carbon also have a hydrogen here. So the first thing that we do is we make a Wittig reagent in situ. Okay, this is not usually it's something you make really quickly and then you go ahead and use that. So a Wittig reagent is something that we call an ylide. Isn't that a cool word? Y-L-I-D-E. Ylide. It kind of sounds like it's in some rap video, right, or rap song. It's an ylide. What does that mean? Well, it means that there's a positive and negative charge on the same molecule at the same time. So this carbon right here has a negative charge, and the triphenylphosphine has a positive charge. And I show you later down here that yes, it can form a double bond instead, However, actually, this is a little bit more stable. So you see it, the illid is. So you see it more in the illid form than in the C double bond P type of form. Anyway, when we connect that with a ketone or aldehyde, what ends up happening, I'm going to use a different color here, is this guy right here basically replaces where that oxygen was on your ketone or aldehyde, which is an awesome new way of making carbon-carbon bonds. And then you also have the double bond that you can do something with. So you make a new reaction, you make a new carbon-carbon bond, and then you can still do more, which is super, super awesome. So Wittig reactions are fantastic. Let's look at the mechanism. Realize that first we have to form the Wittig reagent or the illid, and then we actually are going to use it. Now, before we get to that too much, I want to talk about something called N-butyllithium. N-butyllithium is just a butyl, 1, 2, 3, 4 carbons, and that's got a negative charge on the end. And then lithium, positive charge. Needless to say, that is a very, very strong base right there. And it will rip off hydrogens very quickly. This is a highly reactive reagent. It's very dangerous to use. You have to make sure that you know how to use it appropriately in the lab. And that is one drawback of this reaction. So let's start by using that alkyl halide with triphenylphosphine. We have a simple SN2 type of replacement where the electrons come over from the phosphorus and it kicks out that halogen, whether it be bromide or chlorine, whatever it may be. Next, we take the N-butyllithium, and I drew it on the other side just to make sure that you all could see where that electron was coming from. So I hope that's okay. Those electrons come and grab that hydrogen. You have to have something that's a really strong base to remove that hydrogen, right? Because that's not something that normally you see. And the electrons go back to that carbon. So that's where we have the negative charge come from on carbon with the electron pair. Now, technically, this can undergo a resonance, but as I said, this is not as stable, believe it or not, as the illid form where you have a positive and negative charge there. So the reaction, if you set this up properly, is actually really pretty easy to deal with. So here's the way that you have to think of it. The triphenylphosphine here is going to end up with that oxygen. So they pair up. And then the two carbons pair up. And so keep them on the same side. The negative charge of the carbon from the illid is attracted to the carbon in the carbonyl because it's partially positive. And then the double bond, one of those electron pairs come over and connect to that triphenylphosphine. So you have this square type of intermediate. And then they kind of like flip and switch over. So these electrons go down, these electrons come up. And that's what is going to make the new double bond here and double bond here. Okay, not to confuse you with that, so let me take back. Okay, and so the carbon-carbon double bond is the final product that we care about. You also end up connecting the O with the phosphorus. And so I tried to color code this so you could sort of see what was going on. The carbon that has the C-double-O bond that's in blue over here is where this ends up. And then we also have the carbon from the triphenylphosphine, which really started off up here as your alkyl halide ends up here. Okay, there's more fine details to go through with that, but maybe you can catch that in your reading rather than going through that in too much detail right now. main thing is I want you to know that this reaction happens and know how to deal with the mechanism as well. Okay, and deal with it with synthesis. We need to be able to do problems with this with synthesis as well. Thank you very much.